There's two exact sciences I was taught in high school. Math and computer science.
Computer science is a subset of mathematics.
Correct.
Wow.
Okay.
So, Alex, what are we doing for the summer? Like, are we going to continue?
Traveling.
Okay.
Yeah, I don't know.
Whole summer?
Yeah. I never knew I was so good at shuffleboard. Okay. What was the last thing? Ah, yeah. So we ended by proving that snack is a zigzag. Okay. So we have this is Derek, by the way. Okay. Yeah. So we said that if you have an exact sequence of complexes, right, which really means that you have an infinite two-dimensional diagram like this, that commutes and all the rows are exact, then we can construct a long sequence in homology like this, and then H(n)-1 of A, etc. This is the connecting homomorphism. That's it. So, okay, the next proposition is the following. So like the natural thing when you construct something like this, then the natural question to ask is, how does this delta, for instance, depend on the initial sequence? So in particular, we can apply a morphism, right, to that sequence, which really means in the category of exact sequences of complexes. So, you know, yeah. So we have two exact sequences and we have some morphisms relating them. So let's call them F, G, and H, such that all of this commutes. Of course, this F, okay, so we assume that these guys are all chain maps, which means that if I draw this out into the third dimension, then all these Fs also commute with the differentials in the complexes. The question is, how does, is this also preserved by applying this morphism? In other words, does this delta have a functorial property, which we also call naturality, right? So this is called naturality of delta. If we can produce another commuting diagrams with long exact sequences. So the statement is, if you have this, then you have this long exact sequence. Okay. And then A prime should be A. And then here, it's just the descendants of these chain maps. Of course, G star So the claim, okay, and here we have the delta constructed by zigzag lemma for the first sequence and the delta prime constructed for the second sequence. So we claim that this commutes. Okay. The fact that these two rows are exact, we already know, so we just need to check that it commutes. I thought of a name for this because we like snake lemma. This is probably like tapeworm lemma. Okay. Okay. So how do we do? Well, this is a three-dimensional diagram, which I'm not going to draw. Again, it's one of those things that's easier to do in LaTeX somehow than on the Blackboard. But let's think what we really need to prove. So commutativity of these two squares with f and g and h is just a definition of a chain map. Okay. So the only thing that we really need to check here is the commutativity of this square. So we need to check delta prime h star equals f star delta. Okay. So let's do this. So let's pick a C and Hn of C here. Actually, colored chalk would be good. Yeah. Oh, I think it's too late now. So we must show that f star delta of C equals this. Of course, this is the same as class of H of C, right? All right. Okay, so first of all, we can choose a B in Bn such that P of B equals C, right? Because that's an exact sequence. So P is projective, surjective. And yeah, it's like P projective. Okay. Then delta of C is going to be A, where I of A equals D of B. Right, because the square with the differential commutes. So what's the quickest way? Okay, well, delta of C equals something, right? By definition of delta. What would that something be? It is we are in Bn right now. Yeah, A is here, of course. Yeah, A is here. And then it has to be such that its image here is the same as D of B here, right? That was by construction of delta. That was by definition of delta. Right, it was like this diagonal motion. What do you mean? Well, yeah, but if you just truncate, right? It's like ABC, we go like this, and then back. So that's basically that property. Okay, so therefore, f star of delta of C is going to be f star of this, which is f of A. And let's stop here for now. Now let's look at the other side of the equation, right? So we computed this. Now let's compute that. So H is a chain map. Therefore, I didn't give all the names that I needed, Q and J. So Q of G of B equals H of G of B equals H of C. Okay, something. What this means is that we can use G of B as a pre-image of H of C, obviously, in B prime. So G of B, pre-image of H of C, B prime. So again, by construction of the of delta prime applied to H of C, right, is going to be the same as differential applied to G. So it's going to be A prime where J of A prime equals D G of B. Shut up. Infinite amounts of spam. Oh, I pressed it 5 times or something. Decided to call 911. That's how much I hate them. 911. I'm getting too many calls. Okay. D of G of B. Does this make sense? So this should be the same as pretty much the same as earlier. Okay, so we computed this. But J of so now I'm using again commutativity of the square that involves JF and GI to write that this equals this. I of C. What is I of C? I of C is D of B, again in the complex, right? D of B. I can't remember. Let's look at this. This is J star. This is P star. I'm taking J of F. Oh, did I screw up notation? Yeah. Okay. Let's see if this makes sense. Of and here is D of B, yeah? Because I of A equals D of B. Okay. So this equals J of A prime by over there. Okay. So what does this all mean? But J is injective, right? J is injective because it's the first map in the exact sequence. In the second exact sequence. So therefore, F of A equals A prime. But therefore, delta prime H star of C, which was A prime, is now class of F of A, which is the same thing that we got there. So, okay. Maybe it's not obvious why a statement like this would be useful, but it is actually very useful to know that this construction is natural with spectromorphisms between exact sequences, and we're going to use it at some point. Okay, here's a what? Okay, so here's, I'm not going to prove this. It's a more or less simple exercise. Algebraic Meyer-Vittori sequence. Just look at that theorem and set, so in the last proposition, let's say H star is also an isomorphism in homology. Then there's a long exact sequence like this. Hn of A prime plus Hn of B. And then Hn of B prime minus 1 of A, etc. So what stands here is this operator. Oh, I missed one term. Delta. Okay. So what stands there, delta is delta H star inverse Q star. Okay. Just need to check that this is exact. So basically, if you look at the structure, what happens is you take this diagram, and H is an isomorphism. So we go like this. We go from here, then into the sum of these two, into here. Yeah. Hn of A, where? Oh, Jesus. What did I do? I guess I was blind for a second. Okay. Oh, yeah. So this is F star, comma, I star. Okay. And this is, this map here is J star minus G star. Direct minus. Yeah, so what happens is H is an isomorphism. So you go into here, you come into here, then you add these two, you go diagonally into here. And then you use this isomorphism to like skip this part and end up in Hn minus 1 of A, and then do the same thing. We will see later how this becomes, the familiar Meyer-Vittori sequence later in relative homology. Okay. Okay. So now I'm gonna demystify what we did before when proving Poincare lemma with the homotopy operator. So let's see what, how would you define a homotopy algebraically, basically? If I have an infinite chain complex, or two of them, what does it mean for them to be homotopic to each other? Which is meant to be, of course, inspired by the homotopy invariance of homology of topological spaces, like the Rom cohomology, for instance, in which it's definitely true that it's homotopy invariant. Okay, so first of all, let me define maps of degree P. This is just a map between two chain complexes such that each Sn goes from Cn into Dn plus P. chain maps were degree 0. But unlike in chain maps, there's no requirement on commutation here. So like chain maps need to produce 2 diagrams that, the squares commute. Sorry, 1 diagram where the squares commute. But here there's no requirement that anything has to commute. Okay, so yeah, so the question is the following. We have chain complexes. From here, we can act by the functor hn to compute homologies. Also, if we have chain maps, this produces these morphisms, which we denoted F star, descendants of chain maps. The question is, how much does this actually depend on F, right? How much, if I change, like, how much can I change F without changing F star, basically? That's the idea. So the answer is you can change it by homotopy. Well, I guess in principle, that's not the most general deformation you can make, but it's the only relevant one. No, I'm just saying that's the idea. But of course, the deformations that leave F star invariant are deformations that leave F star invariant. There's no other. Then you should be doing set theory. Okay, so let's say we have 2 chain maps. 2 chain map. F and G. We say that F is homotopic to G if there exists a map of degree +1 from B to C, such that Fn minus Gn equals Dn plus 1 Sn plus Sn minus 1 Dn. So let me draw a diagram that illustrates this. And then C plus 1. We have F and G, D, D, etc. C. Okay. So what we want is an S and going this way, minus 1 going that way, etc. Such that such that Sn equals the difference of the 2 maps that you get by composing a differential with either F or G, right? But again, there's no commutativity here in this diagram. At least not in these triangles here. So theorem. This definition is useful. So homotopic chain maps induce isomorphisms in homology. Isomorphisms in homology. The proof is trivial because we've already discussed how it works when we proved Poincaré lemma. The proof is let's say Z is a cycle. dz is 0, therefore, and so f of z minus g of z is going to be equal by d Sn of z minus 1 dz, but this is 0, So if I take the class and homology of all of this, this is 0 because this is exact.
Sorry. Doing proofs for the array lemma and stuff. It didn't matter what the sign between D and H was and all of that was.
I mean, that's just redefining multiplying S by plus, minus 1 to the n or something. Yeah, it's obviously the sign doesn't matter here. Or any coefficient for that matter. Okay. Also, a couple words. A complex is called acyclic if all homologies are 0. So no cycles. It's also called contractible if there exists chain map if there exists a homotopy between the identity on C and the 0 morphism on C, right? So by a homotopy, you can convert C to something that has a trivial homology. And also, we say that C and D are two complexes that are quasi-isomorphic. If there exist two homotopies in both directions two chain maps in both directions whose compositions in both directions are homotopic to identity. Okay. Was there a question? Yeah. And another related thing is homotopy equivalence. I screwed up. It's easy to confuse them, and I did just that. So homotopy equivalence is what I just said. Quasi-isomorphic is if there exists a chain map such that F star is an isomorphism. Okay, not the same thing. Yeah, right. Yeah. Okay, so this is the end of like the general homological algebra stuff, and now we start the second type of homology theory. This is the most common one, probably because it's the most general one on topological spaces. And so we will do this in a lot of detail and then discuss like how, based on what we learn here, we can come up with other theories. Okay. So like the Ram cohomology, for instance, we use differential forms. We needed differentiation explicitly to construct it. So that only works on smooth manifolds. The simplicial homology was you needed to be able to triangulate whatever you're trying to compute. So for instance, differentiable manifolds have that property, but topological spaces in general don't. The most general class that has that property is probably CW complexes, right? But usually people don't use cellular, don't use simplicial homology for that then. they use cellular homology, which is very similar. But this will work for arbitrary topological spaces at a cost, of course. So definition, let's make delta n the standard n simplex in Rn. I guess Rn plus 1 by definition. You remember what this is, right? Yeah, just take the basis in the convex hull. Okay. Let's make X topological space. Then a singular and simplex in X is a map sigma from delta n into X, which is continuous. So continuous. That's all. Okay. So singular, it's called singular because there's no requirements on this continuous map. It doesn't have to be injective or an embedding, nothing, right? It can collapse delta n into a point, whatever. It's still a singular and simplex. So then the group, the group of n chains here is just going to be free generated by all sigmas. So this is the cost that I was talking about, right? Because there's uncountably many of these sigmas, and therefore this group is just insanely large. Yeah. Just formal sums with integer coefficients of these sigmas, yeah. I mean, you can think of them, right? You can think of the image of a sigma as like an actual subset, and then it's like a linear combination of subsets, more or less. Yeah, free abelian. Oh, yeah. Homological algebra, we don't do non-abelian. Okay, and sometimes we'll write Cn singular, just you know, when we compare it to other types. Okay, so to define homology, we need the boundary operator, and of course it's defined exactly the same way as in simplicial homology. So we have delta n 1 of x, delta of a sigma is just the sum minus 1 to the I, or I of sigma restricted to the faces of the standard simplex here. So it's E naught, E I dropped, and then, okay. There, you have to note here that because each face is itself, okay, so sort of formally, we have to identify each face of an n simplex with a standard n minus 1 simplex. And then this will be a singular n minus 1 simplex. Right? So you identify it with a standard n minus 1 simplex just by dropping this and preserving the order. Okay. So h of x, kernel dn, image dn plus 1. So the question is, this is uncountably large dimension. This is uncountably large dimension. What do you get? What do you get as a result? Well, of course, in principle, you can always construct pathological spaces for which this is arbitrarily big. But the ones we care about is it's the same as any other, like the cohomology, etc.
So for for manifold triangulation, these groups contain, in some sense, the homology, and that was the equation maps.
Yeah. Yeah, sure. Yeah. Free abelian group, right? Yeah. Other coefficients you just tensor multiply by whatever. But we'll do that later. Again, so the general idea is that you don't really need to know much about groups with coefficients, homology with coefficients, because if you know the one with z coefficients, then everything else can be computed from it. We'll have a theorem about that. Okay. So, I mean, they're useful. They are objectively useful, but it's just, I wouldn't be worried that I'm not discussing it right now. How large is what? Yeah. What do you mean? You can always map, right? Yeah. Okay. So as usual, the first proposition we prove about these things is computing the zeroth homology group. So if X consists of L path-connected components, then H0 of X is isomorphic to Z to the L. Okay. How to prove? Did we construct this augmentation map before? We didn't, right? Okay. Did we prove this for simplicial? The statement for simplicial homology. Did we prove it? Okay. Yeah. Well, yeah. Well, okay. So the proof there is actually pretty much identical to this one. So in any case, so let's take L equals 1 because everything else should be obvious that it's just a direct sum of a bunch of z's. So we have H0 of X is C0 of X because everything here is a boundary divided by image of D1. So what's a singular what's a singular zero chain? It's just a sum, a formal sum over a finite number of points. Okay. Where an I, R, and Z. E, I, X. Let's define this map epsilon from C0 into C. It's called augmentation map by epsilon of a linear combination of points is just equal to the sum of these coefficients. Okay, so it just counts the total sort of multiplicity. This is surjective as long as X is not empty, right? Because as long as you have at least one point, you can generate an arbitrary integer number from this. Then we claim that the kernel of epsilon is exactly that image of D1. Right, so that's exactly what you were noting, basically. That the sum of the coefficients in front of the points has to be 0 for that to be a cycle, a boundary of a one cycle, one chain. So first of all, clearly image of D1 is in kernel of epsilon by definition of D, because every point will come in with a plus and a minus twice in the sum. Right? That's not true, but there's an equal number of points for each coefficient with opposite signs. That's what I should say. Okay. So this is true. For the reverse direction, suppose epsilon of a sum is 0. Then we can choose path. We can choose a path gamma I from some arbitrary base point x0 to each of these PIs, right? So just choose a path because x is path connected, right? I assume that L equals 1, so x is just path connected. So we can always choose a path for each PI like this. And then it's easy to check that the sum of Ni gamma I, its boundary will be Ni PI. Why? Because the coefficient in front of x0 in here will be minus sum of ni's, which is 0. Right. So therefore, kernel of epsilon is contained in image of D1. Okay. So if these are the same, then this is like that. But you know, it's obvious that kernel of epsilon is co-rank 1 in the set of all chains because it's just one linear constraint. So the answer is Z. Okay. And now another simple statement, which is, so we can compute the zeroth homology for any space, but we can also compute all homologies for a space which is 1 point, right? So if x is a point, then what do you think? Huh? Oh, okay. So let us prove this. So first of all, for any n, there's only one singular n simplex, right? So for any n, there's this unique sigma in Cn of x, right? Yeah. So d, let's call it sigma n. So the boundary of the sigma n is going to be -1 sigma n minus 1, right? Because they're all the same. So this to the I, sum over I, right? So the answer, so the value of the sum depends only on whether I is odd or even. And so this goes from 0 to n. So there's n plus 1 terms, and therefore it's odd and sigma n minus 1 for even n. So therefore, the chain complex, you know, the chain complex looks like this. So C0 is Z, C1 is 0, C2 is Z, etc. Oh, sorry. Yeah. They're all Z. The morphisms, right? D is either 0 or isomorphism. Okay. So Z, then this is an isomorphism, Z, this is 0, and then 0. Okay. Like that. No, I mean, yeah, but just compute homology. You need the kernel of this divided by the image of this, Z divided by Z. You need the image of this, the kernel of this, which is 0, divided by whatever is 0. Okay, so except for n equals 0, of course, which gives you Z. What do you mean? Yeah, that's the next definition. So, so this is called reduced homology. Any sort of homology theory that is entirely trivial for a point is called reduced. So here we can construct it this way. H and tilde is the notation, is the homology of the augmented chain complex, where you take the normal chains, then you add one more Z over here, and this is epsilon. Okay. So then this way, H and tilde of a point is just all 0 for all n. And for spaces that are not points, you can show easily that H0 of x is just H0 tilde of x plus Z. So it basically just subtracts 1Z from this one. Yeah. Oh, you want connected components? Not with this homology. Okay. Okay. So this is the basics of singular homology. And now, and probably, has it been less than 1 hour? I'm actually surprised. Yeah, but where? No, we did. But that was just a construction, right?
But the fact that that path is the image of sigma.
Yeah, the fact that those paths are exactly sigmas in that.
It still doesn't. Like if sigma wasn't restrained to be continuous, it would still have continuous.
So if you take all maps, then the only thing that matters is the cardinality of this, right? So all the homology is greater than one, which would be the same.
Yeah. Okay, we will definitely use continuity just now. So like all of these properties that we're going to discuss now would not be true without continuity. But yeah, for the basic definition, I guess it's not necessary. So the first property is familiar homotopy property. The statement is the following. If I have two continuous maps between X and Y that are homotopic to each other, then they induce isomorphisms in homology. And F star, sorry, the same isomorphism, the same homomorphism in homology. Okay, so homotopic means the same in homology. In your mind, you always want to set one of these things to identity or something. Okay. Hn of X, Hn of C, right? So if two maps are homotopic, then their descendants in homology are the same. Of course, what does this F star do? How is it defined? F, how does F act on chains?
Yeah.
Just composed with sigma, right? Yeah. And so this F star, same thing, represents this. Okay, so in particular, homotopy equivalent spaces have isomorphic homology. That's one consequence. So for like de Rham cohomology, this was a pretty easy consequence of the proof of Poincare lemma for us. Right here, we don't have those tools, so we have to prove it more algebraically. So the idea is because we are talking about homotopy, that means that you're basically like adding an extra dimension and then deforming the images of these simplices, right? So what you end up actually working on, the space that you work on, is delta n times the interval. This I is just 0 to 1, okay? But this is not a simplex anymore. So what we need to do is subdivide this into simplices. Okay. Subdivide this into simplices. So the way you can do this, so let's imagine a two-dimensional case where there's a triangle, and then this is just a prism, right? The way you subdivide is the following. So let's call this like V0, V1, V2, and W0, W1, W2. Let's look at these n+1 simplices, right? So this is an n+1 dimensional object. So we want to subdivide it into n+1 simplices. The way you can do it is V0, etc. to Vi, then Wi, and then etc. through Wn. Right. So for instance, V0, let me change this. V0, V1, then W1, and then W2, right? So this this thing would be the tetrahedron, and then I also need to draw that line. This is tetrahedron. Okay. And then you can check that as you change I, once you go over all I's here, that's like a disjoint union basically of tetrahedra that make up the whole prism. Okay, so that's the technical bit that we need here. Now we have the homotopy, which is a function from X times the interval into Y, which is F, let's say F in the beginning and G in the end. And let's say we have a singular simplex in X. Then let's form a composition of maps. So we do F composed with sigma times identity, right? So I take sigma multiplied by identity on the interval and then apply F. So that basically creates this deformation of the singular simplex in Y. So this goes from delta n times I into X times I and then into Y. All right. So we can define prism operators. Oh yeah, how do you prove that something on homology is the same? You construct a homotopy between the chain complexes, right? So we need homotopy operators. Here they are called prism operators. P is from Cn of X to Cn plus 1 of Y. As promised, right? This is supposed to be a map of degree plus 1. Defined as P of sigma equals minus 1 to the I, F sigma times identity, and then applied to all of these subdivision simplices. Oops. V0, I, WN. Okay. Okay. That's all. So now you just need to check that G star minus F star equals GP plus PT. This is just some stupid computation that I'm going to do. But just like on Grelum, I guess we skipped all of them. So the idea, it's actually easier to interpret this equality if you put dp on the left, and then you have dp equals g star minus f star minus pd. So this has like a geometric meaning, which is that the boundary of the prism equals the top delta n, which is represented by this g star, because f restricted to the top is just g, and then minus the bottom, which is f star, and then also plus the sides, which is the subdivision of the boundary. Right? Yeah. So the proof of this is actually very easy. It's just apply this, expand this identity, and use the fact that G and F live on the top and bottom of the prism. Okay. So one corollary from this is if X is contractible, then the reduced homology of X is all 0. Yeah. I mean, in part, that's why cellular homology is like a big thing. You use disks there, disks glued to each other by some maps. CW complexes. They're kind of a generalization of simplicial complexes. It's just turns out that many more. Why am I erasing this? Many, well, fine. Many more topological spaces can be realized with CW or are homotopy equivalent to whatever the CW complexes than simplicial complexes. So triangulation is too strong. Okay. So sometime later, we will discuss the axioms of homology, which are the idea of, like, if you want to define, if you want to understand what you should require from an abstract homology theory on topological spaces, then these properties are two of the things that you definitely want to require. So you want it to be homotopy invariant, and you want it to be to have the excision property. Excision property. So the excision property is something about like cutting out pieces of the space and seeing how the homology changes or doesn't change. Okay. And in fact, so this is going to be the idea behind the Meyer-Vittori sequence for singular homology. Okay, so what's the basic idea here? Let's say we have a topological space and an arbitrary subset A. It doesn't have to be open, just arbitrary subset. Then you might ask, we have the groups. We have this group. X over A just means we identify all of A into one point, right? That's the quotient by a subspace. So if you identify all of A into one point, how does the homology change? That's like one thing that you can compute. Another thing is Hn of X divided by Hn of A. Right. So the question is like, how different are they? And from some thought experiments, you can probably quickly realize that that depends on the homology of A. That depends on, how many holes does this operation kill? Okay. Okay, and so the difference between these two things it turns out to be measured by the relative homology. What do I mean by that phrase? I mean that there's a long exact sequence that contains this, and then the relative homology, and those, and then minus one, etc. Right? So that's what I mean, the difference between these two. Okay, definition. Would have been too nice to have a short exact sequence, right? Then that would be literal. This factored by that equals relative homology. Okay, so definition. Let's say A is an X any topological space. We have Cn of A. This is a subgroup of Cn of X. Right? You can treat this as a subgroup of Cn of X by just including. Then also the boundary operator on Cn of A, of course, maps into, again, Cn minus 1 of A. Right? So it's consistently defined on only chains on A. Therefore, we can factor one by the other and preserve the definition of the boundary operator on the factor. So define Cn of X comma A as the factor, Cn of X Cn of A. And we have the boundary operator from Cn of X A. Okay. So the homology of this complex is the relative homology. Obviously. Okay. And now, because this really sort of depends on two different topological spaces, this is a functor on not the category of topological spaces, but the category of pairs, right? Remember, I defined category of pairs of sets a long time ago, where you have a set and then you have a subset. You can do the same for topological pairs. So then Hn acts on topological pairs into abelian groups. Okay, so proposition. Exact sequence of a pair. Huh? Yeah. So yeah, if I have two pairs, x a x prime a prime, then f of a has to be an a prime. Yeah. So that factors with respect to these are well defined. Okay. So turns out that there's an exact sequence for any pair of homologies. Obviously, this is an exact sequence by definition. I was sure I fixed this typo. Okay, right, that's just the definition of this. Therefore, it produces the long exact sequence in homology. There's nothing to prove, it's just an application of Sneck lemma. HNFA. Okay, so this is easy. And the same sequence exists in reduced homology also. Immediate corollary of this, or two. Number one, if A is contractible, then what? Right, so this is 0, this is 0. Therefore, this is a so. Okay.
But that's only if n is greater than.
So let's. Yeah. Then. Well, yeah. Okay. Yeah. Let's leave it. For one should work.
Even for n equals 1, n minus 1 of a becomes 0.
Okay. Okay. If X is contractible, then what? So this is actually very useful, surprisingly. Then what? Hn of A is isomorphic to the other one. Right. So this is very cool, right? So for instance, you can take the circle, embed it into R3, and you can compute the homology of the complement. You know, if you take R3 and you contract the circle into one point, like what is the homology of the result? Very easy, right? You can compute it from the homology of the circle. Yeah, similar. Okay. Of course, I mean, you have to think about how this is actually related to the homology of the complement. Right? This is not the same operation, but yeah. Okay, this is all clear. Turns out that there's another. Oh yeah, one sec. So the connecting homomorphism here, you can realize its geometric meaning easily. So what is the geometric interpretation of elements of relative homology or chains, relative chains? How are they different from just chains in X? Right. Yeah. Yeah. So let's say this is A, right? Yeah. So, okay. So for instance, if this is A, like a stick, an interval over here, right? Then normally this chain would not be a cycle in X, but relative to A it is, because it differs from a cycle only by a chain in A, right? That's the idea. So how can we do this? Well, cycles relative to A are in particular chains in X, right? Although not cycles. So you can think of these as chains in X. Yeah, but each representative you can take and think of that as a chain in X, right? And then on that you can act with the boundary operator, right? And get a boundary in A. So, right. Because initially it was a cycle relative to A, therefore its whole boundary in X must be in A, right?
So this says basically that boundary operator acting on representative classes, they're all equal.
Say it again.
So if you take these, because you have this equivalence class of many different chains, and so the boundary operator acting on them is because we need the boundary operator to act.
It's not homotopy equivalent. It's just you need to check that it's independent of the choice of representative.
So you get exactly the same.
Yeah. Yeah, like in homology, that's just a map. All right. So there's another exact sequence which is sometimes useful for topological triples. So you can have XAB, where B is an A is an X. Then you have this exact sequence. Should be also obvious. C X A C X A. Chains in A relative to B can be injectively mapped into chains in X relative to B, and those are exactly the ones that are killed by projecting onto A right now. So this produces a long exact sequence. I'm not going to write it out. You know what it looks like. Okay, so opposition. This is the main theorem here. It's called homotopy property. Oh, sorry, not the main theorem. We already did homotopy property, but this is homotopy property for relative homology. So if two maps to YB are homotopic in maps of pairs, just homotopy at every moment in time, it has to be a map of pairs, right? Then F star equals G star. And okay. The proof was just saying it's an exercise. Just think about it for a second. Okay. So the next is excision property. And the basic idea behind it is this Meyer-Vittori sequence approach to computing homology that I mentioned, I think, last time, where Meyer-Vittori sequence relates homologies of two subsets that cover a space to the homology of the entire space and the homology of the intersection of those two subsets. Right? So the idea is maybe if you take a space and you cover it by a bunch of subsets, and you take them sufficiently small so that their homology is easy to compute, or for instance trivial, then you will be able to compute the homology of the entire space by looking at the intersections. And you can always guarantee that the intersections are also kind of simple in some way, or they consist of components, connected components that are each simple, right? Like it was for the circle. Okay, so for that, you need to ask, of course, like how well does homology defined based on like a covering approximate the actual homology of the space. So let's clarify what this means. Let's make this curly U some collection of subsets, subspaces. Again, they don't have to be open here, of X, such that the union of the interiors of these U alphas covers all of X. And let Cn U of X should be self-explanatory. So this is the set of chains such that the image of each simplex is contained in one of these sets. Okay, so you're not allowing simplices that are too big. So this is a subgroup of Cn of X, obviously. And the boundary operator is also well defined on this. All right. So we can define Hn U of X. And so the question is, how different is Hn U from Hn? Okay. Did you space out? Okay, so we take a cover of X by some subspaces, and we consider only chains where each simplex lies within one of these subsets. Right. So you cover. And you want your simplices to be small enough to fit inside one of these. Not only small enough, but positioned right. So that's just a subgroup of the space of all chains. The boundary operator is still well defined on these guys, so you get some homology defined this way. Okay, so the question is, how different is this from the actual homology of X? And the answer is not at all. Who would have thunk? So let's say we have the inclusion of these U chains into all chains. And then the statement is this induces isomorphism. Okay. So the proof of this is super long. And I'll just try to outline maybe the steps. The steps that you need. The idea is, again, we're trying to prove that some homologies are the same. To prove that, we need to construct a homotopy operator between these two chain complexes, right? What would this homotopy operator, what could it be? Right? A homotopy equivalence, even, right? So what we really want is to construct a map in the opposite direction here, which is homotopy inverse to I, right? Such that the composition of I and rho and I are homotopic to identity. What could this be, right? Take a chain. How do I produce a chain out of it that consists of small simplices? How? How can we turn the simplex into a bunch of smaller simplices? How? Yeah. Barycentric subdivision of delta of simplices. That's number one thing that you need to do. So what this is you just take a simplex. Let's say it's this. I am working in like a Euclidean space right now, so Rn. And then let's denote this barycenter by B. So it's just that. And then the barycentric subdivision consists of these things. So let me draw. Where this is iteratively defined as the barycentric subdivision of a face. So this is in the subdivision of a face of sigma. Okay.
What is the number of vertices in both the same? The barycentric subdivision should have 2
And n+1 in both cases, right? This is n+1 points. So these are both n simplices. Okay. So like a triangle, we need to do this iteratively, right? So like the barycentric of a point is only a point. The barycentric subdivision of this consists of the barycenter of this interval, which is this, and then connected to one of the faces, of this interval, which is this and this, right? Therefore, you get 2 intervals. Now, for the triangle, you take the barycenter, and then you add one of the elements of the subdivision of the faces. So, like this, that defines this, or that defines that, etc. Iteratively, you can do this. It turns out that it's useful to know that the diameter of subdivision of sigma is bounded by n over n+1 of the diameter of sigma. Okay. The reason this is useful is because this is less than 1. Therefore, by iterating subdivision, you can make them arbitrarily small. This is all in Euclidean space. Then you consider first linear chains, which means chains in also in some Euclidean space produced by linear sigmas, right? So singular simplices that are linear on these standard simplices. And then from there, you inductively sort of construct some homotopy operator for, you construct this row, which morally is just an iterated subdivision, right? And you can show, so because of this estimate, for each simplex, there exists a minimum number of subdivisions that you need to do to make it fit into this cover U. And then that lets you define this row just as, on each simplex, it's defined as the minimum number of subdivisions to fit it into U, okay? To fit every piece into U. And then once you have this row, you need to check, first of all, you need to check that I composed with row and row composed with I are homotopic to identity. And for that, you need to construct 2 homotopy operators. Actually, one of those should be obvious. So just 1 homotopy operator. And that's kind of nasty, so I'm not going to do it. But it's some, iterative procedure like this, some inductive definitions. But it can be done. What's that?
So we need to construct homotopies that subdivide the simplices back to the right?
Yeah. Mm-hmm.
Okay, so that would just involve like choosing one subsimplex and then
No. Wait, what do you mean? How to go in this direction?
Well, when we construct the composition, we need to show the homotopy to the identity.
Which composition?
So I compose with row.
So first row and then I?
Yeah, so then, because then what happened is we include a simplex in the subdivider.
Yeah. I mean,
So we need to unsubdivide it somehow, right?
you don't need to. It's just, I mean, that should be obvious that that's homotopic to identity. I guess that was your idea, right? That what does that homotopy operator looks like? Yeah. Should be something. Yeah. I don't think you need to unsubdivide anything. Just this should be more obvious without maybe even homotopy operator. Okay. Let me do excision and then finish on that because we have so many people missing today. So yeah. Okay, so this is excision. Let's say we have, oh god, a bunch of spaces. X, such that the closure of Z is in the interior of A. Then the inclusion, the claim is that the inclusion of X minus Z, comma A minus Z into X comma A, which is well defined because this is a subset of that, induces isomorphisms HM X minus Z A minus Z. Okay, for all n. Equivalently, another form that is sometimes helpful is if you have A and B X such that the interiors cover all of X, then you have the inclusion B and intersection into X comma A. And this induces isomorphisms of this. To go from one to the other is just some renaming of these sets. Specifically, E equals X minus Z and Z equals X minus B. Right, because in this case, A intersect with B is just A minus Z. And the condition that Z is contained in the interior of A is equivalent to X. Okay. So with this, those two statements are equivalent.
So by choosing the contractible A here, this is saying that we can remove points or remove points and there's still an isomorphism.
Let's see. What's contractible?
So we can choose A to be contractible.
Here, A. Right.
And we can basically say that this inclusion of X over Z to X is an isomorphism from X over Z.
Yeah.
But would that be the case like if we take this and we remove a point, it's homology
Remove a point. What do you mean by remove a point?
So if we let say X be a disk,
yeah,
Z be a point.
Okay. Yeah, the problem is if that point is inside of A, you kill A by this, right? So that hole disappears once again. So it's, yeah. But yeah, the interesting case is when Z equals A, right? When,
Okay, so the relative homology sort of already contains information about what happens if you
I guess. Okay, but the proof of this is pretty easy once you have the previous thing. So we have, so let's prove the version with A and B. Okay. So our cover is going to be just A and B. And we have the chain groups C and U, which are sums of chains in A and chains in B. Okay, so it's more or less just a direct sum of Cn of A and Cn of B, but with some identifications, inclusions into X. Because we know that that theorem can be proved somehow, there exists a homotopy operator D such that this is identity minus I composed with rho. Right. And all maps here, just by construction, take chains in A into chains in A, chains in B into chains in B. So this is all well defined on factors. So this is induces same formula on factors by Cn of A. Okay. So what will that give us? Okay, so we have the inclusion Cn U of X by Cn of A. Cn, well, yeah, the U is redundant. Here, Cn of X by Cn of A. We have this inclusion. And this inclusion satisfies the same identity with some rho. So therefore, this also induces isomorphisms. Isomorphisms in homology. Also, the map Cn of B by Cn of A intersect with B into Cn U of X Cn of A. What is this map? Also induced by the inclusion. Induced by inclusion B into X. This map is also an isomorphism because B is already one of the sets in U. Okay, so this is already an isomorphism. So this is isomorphic to this, and the composition of these two maps induces an isomorphism in homology. That's the whole proof. Yeah. Let me stop here. We'll discuss the consequences next time. No?
Next time I will print the notes correctly.
No.
Not allow the printer to sass me.
Just slap it. Have you seen that meme with Newton?
Newton slapping a printer?
No, a car.
No.
Do you know the meme with slapping a car?
No, it's not true.
Look at this bad boy. Yeah, Newton slaps car. Car slaps Newton back.